In this video, we will go through how to make an ASV table and remove chimeras in Chimera using the DADA2 package. So after this video, you will know how to create an ASV table and how does it look like, what are chimeras and how you can remove those, and then finally we will go through the parameter options and the resulting output files and how they look like. So what is an ASV table and how to create it? So in Chimera you can create it with the tool make an ASV table and remove chimeras. And it uses the make sequence table command of the DADA2 library. And as input you need to give either the RDA object, which was created when the paired end reads were merged into contigs with DADA2, or so if you have paired end reads, this RDA object should be given. Or if you have single end reads, you should use this object created with the sample inference tool, so the second one. And what is an ASV table? I will show an image in next slide, but for now I could say that it's very similar to the OTU table, if you are familiar with that. But all in all, it's used to show the distribution of ASVs in each sample. And the ASV table contains still chimeras, which we will remove after a few slides. So the ASV table looks like this here. So each row, like here, corresponds to a sample, and each column to a different amplicon sequence variant found with the sample inference tool. So ASV1 or ASV2 and so on. So you can find out how many times each ASV was found from each sample. And for now I could just mention that the columns here contain the full DNA sequences of the ASVs. So now we have created the ASV table, but we need to remove the chimeras. In Chimera that can be done with the same tool. And to remove chimeras from the ASV table, the remove chimera de novo command of the DADA2 library is run. But what are chimeras? So in short, those are artifact sequences, which are formed by two or more biological sequences. So chimeras arise typically when an incomplete amplification during PCR allow the subsequent PCR cycles to use the partially extended strand to bind to the template of similar sequence. So that means that then the partially extended strand can act as primer to extend and form a chimeric sequence. So there is two possible ways how the chimeras can be detected with the DADA2 command. So the default option is called consensus, and then the chimeras are identified on a sample by sample basis. And then if an ASV is identified as a chimera in most of the samples, it will be removed. The other option is called pooled, and it means that each sequence is compared against the more abundant sequences of every sample. So the ASVs in the sequence table are pooled together for chimera identification. But how does the algorithm identify chimeras? So at first, the function assumes that the chimeras arise from two parent sequences, and those chimeras which are formed by exactly two parent sequences are in this context called chimeras. So Needleman-Wunsch pairwise alignments are then performed to compare the less abundant sequences with the most abundant sequence. And if the less abundant sequence can be reconstructed from two more abundant parent sequences by combining a left and a right segment, the sequence is flagged as chimeric. But let's go through that again in a bit more detail. So at first here, the sequences are ordered by the abundance, like you can see. And the low abundance sequences are compared against the high abundance sequences. And if the low abundance sequence, like here, can be formed by two parent segments, it's flagged as chimeric, like you can see. And then if we are using the consensus method, the default, the chimera is removed if it's flagged as chimeric in most of the samples. And after that, the ASV table is updated, and now it should not contain any chimeras anymore. And as output, you will get those 4 files. So the ASV table is saved as a RDA object. And then the sequence table no_kim is a visualization, which you can see here, of the ASV table after the chimeras are removed. So here the column names are renamed, like you can see, to make the visualization and table to look a bit nicer. So it's renamed as ASV1, ASV2, ASV3 and so on. But no worries, the RDA object, so the first one, contains still the full DNA sequences. Then finally you will get 2 summary files. So from the summary text file on the right side here, you can find how many unique ASVs the ASV table contains, how many ASVs were removed as chimeric, and the distribution of the lengths of the ASVs or the ASV sequences. So as a sanity check, you can check that the lengths looked as wanted. So here the sequences were from the 16S V4 amplicon region. So the read length of around 250 looks great and very reasonable. And then in addition you will get the summary table, so the one in the left side. So to inspect how many reads remained after the chimera removal. So here on the left side, each row corresponds to a sample, and the first columns show how many reads there was before the chimera removal, and the other one after the chimeric sequences were removed. So to note here that it's quite common that many ASVs are removed as chimeric, but most of the reads, so here, should not. So in other words, that means that there might be quite many chimeric ASVs, but those are very low abundance. Most of the ASVs removed as chimeras have an abundance of just a few copies. And like in this example, for example, we found 61 ASVs to be chimeric from the 279 input sequences or ASVs. But like you can notice from this table on the left side, not many reads were removed after all, like just a few. And the most important thing is that we kept most of our reads. So if you would notice here that most of your reads are removed, please double check that you managed to remove the primers from the reads. And especially primer sequences with ambiguous nucleotides can cause that to happen. And I have seen examples where over 90% of the different unique ASVs, so here, are removed in this step. But especially if most of the reads still remained, that should be okay. And you can consider your own data and think how many different ASVs are you expecting on the samples.